Earlier, as we were starting our explorations of optics, I had mentioned that there had been a debate in the physics community that lasted about a century or so over whether light was a wave or a particle. Now, with the advent of modern physics, we say that it's a false dichotomy and that the wave nature tells us the probability of where we would detect the photon. But in the more historic approach that we're taking now, Young's experiment was a very good argument that light was a wave because that sort of interference pattern could only happen if it were a wave. However, there were still issues that people were having to address, and one of the other debates early on had to do with the phenomenon of specular reflection. This is when you shine light off of a particularly shiny, well-polished surface, a mirror. We know that we will see that light bounces off at exactly the same angle it comes in, which is a very compelling argument for the model of light being a particle. So it was up to people like Christian Huygens to come up with an explanation for how waves could have particle-like behavior. This led to what's known as the ray approximation. So remember, Huygens' principle says that every point on a wavefront, let's say we have our wave propagating to the right here, is a source of spherical wavelets that propagate out in all directions. And I've asserted that, without particularly any proof, that the bits of the wavefront that propagate, of the wavelets wavefronts that propagate backwards, will all destructively interfere out. That's something you can prove in a more advanced treatment. But we can look at the bit going forward, and we can see, like right here, we have all of our wavefronts constructively interfering to make the next wavelets constructively interfering to make the next wavefront. And then we can do it again, like so. I won't do as good of a job drawing it here. And this process will repeat as many times as you like, but I'm going to stop drawing here. So what Huygens observed was that since plane waves will always reproduce, a plane wavefront will just make another plane wavefront, you can describe the plane wavefront by erecting a geometric ray that is perpendicular to the wavefront and pointing in the direction of propagation. And this geometric ray gets the clever name of ray, or light ray. So our wavefronts are propagating forward, and what Huygens was able to show, and we will be revisiting, is that some of the phenomena for which it seemed like you needed to have a particle model of light, these rays turned out that they act in a very particle-like way. So let's go ahead and start to take a look at specular reflection. So this is where light reflects off of some nice smooth polished surface. Now, I'm not requiring that 100% of the light get reflected off of it. So what I'm doing here is I am erecting a normal to the surface. And remember, to a physicist, a normal usually does not mean the opposite of messed up. It means a a line that is perpendicular to a surface. In fact, that this is actually, there are two distinct English words, normal. So, you know, when you look in a dictionary and you have two words that have identical spellings and pronunciations, but came into being through completely different etymological patterns, the dictionary will usually give it two separate entries, one with, say, a superscript 1 and another with a superscript 2. In the Oxford English Dictionary, normal 1 is the word that means not messed up, basically, and normal 2 is perpendicular to a surface. So anyway, we know that if you shine light, like say, if you shine a small flashlight, or if you have like a laser pointer or something like that, if you shine light on the mirror, you know, on a surface that's capable of reflecting, we'll have here, whoops, what's called the incident ray of light. And what will happen is some of the light will reflect back out. So that will get called the reflected ray. And possibly, if the material isn't perfectly reflective, some of the light could go through. So for instance, especially if you stand in front of a window after sunset and you've got your lights on, you can see your own reflection in the mirror. Well, the person on the outside, or reflection in the window, the person on the outside of the window can see you standing in front of the window a lot better than you can see your own reflection. So in that case, a little bit of light is being reflected off, and most of it is passing through. The bit that passes through, we will call the refracted ray. And it turns out that the percentage that's reflected versus the percentage that's refracted will depend on the angle you come in at. We won't worry about the refracted part right now. That will come in a couple more video series. But for now, we'll just focus on the bit where we have reflection. And keep in mind, if you've got a particularly shiny surface, like a well-polished piece of aluminum foil or something like that, basically almost all the light gets reflected and pretty much nothing gets refracted. So this angle here that we measure with respect to the normal, this is the angle of incidence, or the incident angle. And this angle out here is the angle of reflection, or the reflection angle. And the law of specular reflection says that the angle of reflection equals the angle of incidence, which is why I marked these as congruent. Now, in the particle model of light, you'd say, hey, that's just like if I threw a super ball off of a wall. We learned in mechanics that light bounces, that the super ball would bounce off at the same angle. But since Young's experiment has shown us that light is much better modeled as a wave, we're going to have to work a little harder to get this result. So here's what's going on with this. So let's go and take a look at our surface that we are reflecting off of. Now, what I'll do here is I will mark our incident wavefront here. So this is just, oops, this is just one wavefront coming in. There's a whole bunch more coming in right behind it, but we're just focusing on one particular wavefront at this exact moment. We're going to take a look at what happens a short time later as this wavefront hits the surface and reflects back. Alrighty, so first thing we can do is we can go ahead and erect our incident ray of light. Incident ray associated with this wavefront, that will be perpendicular to that wavefront there. So, and then we'll go ahead and erect our normal. Sure, I can incident ray coming in like so. And we'll go ahead and label this angle here as theta incident. Now, the first thing that we can note is that since this is theta, if this angle is theta incident here, since the normal is perpendicular to the surface by definition, that makes this angle here 90 degrees minus theta incident. And since this angle here is also 90 degrees here because the ray is perpendicular to the wavefront, that means that this angle here, in order to make 180, would have to be 90 minus theta incident, or theta incident itself. So this angle here is also equal to theta incident, so we'll go ahead and observe that those are congruent. All right. Now, what we're going to do as we apply Huygens Principle here is we're going to look at one point on the wavefront here, and we're going to see where the wavelet that this emitted propagated to sometime delta t later. And at this time delta t, we're going to say that it struck the mirror right there. At the same time, we can follow this one here, and we know that the wavelet would have to have propagated out out in the same distance. So we'll go ahead and label this distance here. This will be equal to c delta t, where c is the speed of light and just delta t is the time it took for the wavelet to get from here to here. Okay, so this will allow us to locate our reflected wavefront. Let's see, what color should we use for that? Yeah, let's do that one. So our reflected wavefront is going to look something like that. And so now we can go ahead and mark out that this distance here, and apparently I didn't draw a very good angle, or I didn't. Let me actually just cheat a little bit and draw the reflected wavefront in after the fact. I think we'll all be happier if I do that. Yeah, that's about the same there. Okay, good. And then we will draw in our C. Okay, well, I tried. This length here is also c delta t. So this distance from here to here and from here to here are the same, making these two legs here congruent. Now, we've constructed our reflected ray here. It's our reflected wavefront. So anywhere we want, we can go ahead and erect a perpendicular to it. Whoops. So I'll just do it right here to mark our reflected ray. Okay, we can mark this angle here as theta reflected. And by the same kind of argument that I made to say that this angle here and this angle here were congruent, we can observe that this is also equal to theta reflected. All right, so now what we can do is we can consider two triangles here. We can consider this triangle right here that I'm highlighting in sort of maroon. And we can consider this triangle here that I'm highlighting in purple. There we go. So this triangle here, this leg here and this leg here are congruent. And this is a 90-degree angle here. That's a 90-degree angle there. And both this triangle and this triangle share the hypotenuse, so it's congruent to itself. So this means that our triangles are congruent by side-side angle. So this means that theta reflected does equal theta incident. Oops. Which completes the proof. So this is one of the few times that you'll see in physics, at least, a explanation that a case where you truly realize that Occam's razor is a guideline and not a rule. Remember, Occam's razor is a guideline in philosophy that basically says when faced with two competing explanations, the simplest explanation is usually the best. But the key word there is usually. The particle model was certainly the simplest explanation, but Young's experiment demonstrated that light is a wave, and so we had to roll with that and figure out how we could reproduce the explanation from the particle model. And this sometimes happens in nature. Now, again, like I say, in modern interpretation, we would say that light has both a wave and a particle nature, so you shouldn't be surprised that the two have to come together in harmony. All right, so let's just work a quick example of this. So this will be a good one for you to just, after I set it up, for you to pause it and give it a quick try yourself. So let's just say we've got ourselves two mirrors, and they are separated by 135 degrees. We will bounce a ray of light in here such that it will rattle off of that mirror, bounce off there, and then, whoops, come out over here. And remember, in optics here, physicists will always measure their angles with respect to the normal. There are good reasons for this, but I don't that have to do with calculus mostly, but I don't really want to get into them here. All right, so we'll just go ahead and erect a couple of normals here real quick. There we go. So let's say that light, the light comes in here at theta 1 incident is 70 degrees. I'd like you to figure out the angle that it reflects off the second mirror at here. What is theta 2 reflected equal to? So go ahead, pause the video, and give it a try. Alrighty, so let's go ahead and work this one out. So by the law of reflection, we know that this angle here and this angle here both have to be 70 degrees. So theta 1 reflected here is 70 degrees. This makes a right angle, so 90 minus 70 means this angle right here is 20 degrees. 20 plus 135 is 155 degrees. And since I need to make 180 degrees in a triangle, that makes this angle here 25 degrees. So again, here I need to make 90 degrees. So if this angle is 25, that's going to make this angle here 65 degrees, theta 2 incident. But by the law of reflection, that means that this angle here is also 65 degrees. As we go on, we'll see that if we have properly curved surfaces, we can coax light to reflect in ways where we can bring things to focus and magnify images and stuff like that. So I'd like to spend just a quick moment, though, on diffuse reflection. So you can do a quick comparison of specular and diffuse reflection at home. If you have a flashlight, say a piece of aluminum foil or just a hand mirror or something like that, you can check out specular reflection just by shining the flashlight on the piece of foil or whatever. And you can see if you make it so it bounces off the foil or the mirror or whatever, you'll see a nice tight spot on the wall. Now, if instead of using something shiny like a mirror or aluminum foil, you were to instead use, say, a piece of paper. Construction paper is great for this because of how rough it is. Newsprint is good, but even notebook paper will work just fine. If you shine the light off of that, what you'll see is that like the whole chunk of the wall behind just kind of glows, but you don't have the well-defined spot you had when you had specular reflection. So what's going on here? Well, what's going on is that the surface isn't smooth. It's rough. So I'm just trying to represent some jaggies here. Now what's happening is that as we see light coming in, we can think of it as being a whole bunch of parallel rays of light. So at every point where it strikes, you will obey the law of reflection. So here, where it hit this valley, we follow the law of reflection. But then say here, when the light is coming in, say closer to this hilltop here, the normal isn't pointed the same way. It's going to always be perpendicular to where the surface is. So this ray of light here is going to reflect closer to its normal there. And similarly, if we have a ray, say, that catches like right on the back side of one of these here, like that, it's going to reflect off very shallow indeed, something like that. And so you can see here we might even end up with a double bounce, similar to what we were just looking at with the two perfect little mirrors. So we'll have to erect another normal here. And so it does that. And oh, hey, look, we're going to have to erect yet another normal to think about what happens there. And so then finally, it comes out. So the fact that the surface is rough means that the brightest part of the spot will land where it would have if it were a smooth surface, so that everything would be obeying specular reflection. But what's happening in diffuse reflections, you're still obeying the law of specular reflection. It's just point by point here. So it spreads out a bit. It's interesting. Sometimes because materials like paper will also absorb light, if you've ever seen like a photographer doing photographing a group of people at a beach or something like that, one of the problems you run into is that the way the light shines in a beach, often the light doesn't go into the subject's eyes very well, and you get these really dark shadows, and it doesn't look in the eye sockets, and it doesn't look very flattering. So a lot of times a professional photographer will have somebody standing nearby with usually a kind of a shiny looking object, and what that is it's actually a rough surface that's been coated with really shiny material. So by doing that, you don't absorb very much light. You reflect it all, but because it's rough, it spreads it out, so it's not obvious that you're shining light into the subject to lighten up their eyes. It just makes it look more flattering for them. All right, so let's finish this video off by thinking about a plane mirror, the sort of mirror that you have in your bathroom that you stand in front of when you brush your teeth in the morning. Oops. So this will be a bit of an introduction to what are called ray diagrams. So first off, what I'm going to do is I'm just plain going to draw our mirror. And usually when we're thinking about how we form images, we'll just usually super duper idealize the object that's getting reflected by where the light off the object is going to reflect by mirror as just an arrow. Now here, I'm going to run a perpendicular to the mirror. This gets called the optical axis. So again, that's just going to be perpendicular to the mirror like so. So now when you look in a mirror, and when you're brushing your teeth in the morning, you see sort of like your evil twin Skippy also brushing their teeth in the morning. And they seem to be mocking you because they seem to be doing it with the wrong hand, but we'll get into that in a second. So first off, let's just locate when you look in the mirror, you definitely see yourself in the mirror. And it turns out that you see yourself as far behind the mirror as you are standing in front of the mirror. So let's go and follow that through. We can do this by saying, well, at every single point on this object, because Huygens Principle says that we can think of this as a source of spherical wavelets, light's just bouncing off of you going every which way. We can pick any point we like and imagine that there are zillions of rays coming off of that point. We're going to focus on this point right at the very top here, just because it's convenient. And there are going to be two special rays that are going to be super helpful for us in figuring this one out. So the first one here is a ray of light that is parallel to the optical axis. This gets the name of paraxial ray. And the other one will be the one that will be aimed to the intersection of the optical axis, which is just usually where we put the bottom of our object, and the mirror. So this one gets called the central ray. Oops. And I think knowing where I'm going to be writing, and go on, stick the label over here. All right, but like I say, those aren't the only two rays in town. There's, for instance, this ray that's heading this way, but that's never going to hit the mirror. There's this ray here that's never going to hit the mirror. This ray will hit the mirror, but it's not too useful for us. Ditto here, that ray will hit the mirror down there, but again, it's not going to be useful for us. So we're only just picking out two rays that are particularly useful. Let me just make those go away so we're less cluttered. So with these two rays here, if we think about the paraxial ray, the first question is what is the angle of incidence of the paraxial ray to the mirror here? Pause the video and get back with me. Yeah, so remember, we always measure these things with respect to the normal. So let me go ahead and draw in the normal here. So here, our angle of incidence is 0 degrees, which means our angle of reflection will also be 0 degrees. So that means that our paraxial ray will reflect right back out. Now here, this one's going to be less obvious. I don't know what this angle is. It's just something. But the thing is we can still follow the law of reflection. And the nice thing here for figuring out the reflected ray is you can just make a dot at this point exactly the same height below right there. And then you know that that ray has to go through that dot. Like so. And that's just a fast and easy way to construct our reflected angle, which we know those have to be congruent. All right, so what is happening is we're seeing rays of light bouncing away from the mirror. Now, this one would never strike your eye. This one, maybe, if you know. But it'll also be the case that even for all of the other rays that we follow, they will follow trajectories that fit in between these. And those will be the ones that hit your eye. And you could use those to locate the image, but these will be easier. So the thing is that since the rays are coming away from, are spreading out away from you, only a small pencil of rays, of reflected rays coming back are actually going to make it into your eye. When you try, your eye will say, hey, these rays are spreading out. They must have come from some point source. Where is that source? Well, what we can do is we can track back where these rays would have originated from. So usually when we backtrack, dotted lines are the way to go. So this ray originated from some point somewhere on here, and this ray, this reflected ray here, originated from somewhere on this line here. So the only place that both of these rays could have originated from is that point right there. Then you can, and so the ones that you really see are going to be again from a small pencil of rays right here that would have originated, that your eye would say would originated through here. But this one's more convenient to locate with. All right, so let's see, how tall is your evil twin and how far away are they? So to that end there, we'll label this the object, and this is the image. Now the kind of image this is it's called a virtual image. The reason it's a virtual image is that you have to look through the optical device in order to see it. If it's what's called a real image, that's one that you can form on a screen. Here, if you were to put a screen behind the mirror, you'd see nothing because there's no light there. But if you look through the mirror, you say, oh, the rays of light all appear to originate from this point, so I see it here. All right, so we'll call this height here h, and the height of the image we will call h prime. We will call this distance here what's called the object distance s. And we'll say that it's greater than 0. And then s prime here will be the image distance. And we're going to say that s prime here is negative. This is following a thing called the left light convention. We will get more into the left light convention in a later video. But for now, the general rule of thumb is that for distances, numbers are positive if you're where the light is, and they're negative if you're where the light isn't. So since the light is not actually on the back side of the mirror, that makes this distance negative in the left light convention. So let's see if we can relate our h prime to our h and our s to our s prime. Well, first off, we know that these are both right angles. And by alternate interior angles, this angle here is congruent to that angle there. So this angle is 90 minus this angle is 90 minus that, means these two are also congruent. And again, we have a side shared in common between this triangle here and this triangle here. So by angle side angle, this triangle and this triangle are congruent. That means that this distance s and s prime, we end up saying that s prime will be equal to negative s. And remember, this is just purely because we are defining this image distance to be negative. And similarly here for the heights, we can observe that the image height, since these triangles are congruent, that means that the image height is equal to the object height. Now, I'm going to define a thing called the lateral magnification. We'll also run into a beast called the angular magnification later when we talk about optical instruments. But for now, we'll talk about the lateral magnification, which is lowercase m, and it is defined to be the ratio of the image height to the object height. Now here, because these are congruent, h prime and h. Now here, because these are h prime is equal to h, this is equal to 1. But I'm also going to cryptically observe that this is equal to minus s prime over s. That's because even with curved mirrors, this will be a true statement. But we'll get into that in a later video. Now, I did say that it appears that your evil twin, when they're brushing their teeth, is using the wrong hand. And this is actually not the case. When people look in a mirror, often they'll say, oh, hey, you know, right and left got flipped in the mirror, but that's not what got flipped. Go ahead and ask yourself what something got flipped all right, but what? Pause the video and get back with me on that. Okay, so what got flipped is front and back. Since the image distance is always, well, minus the object distance, bits of you that are closer to the mirror are going to be, their image will be closer to the mirror as well. Bits that are farther away will be farther away. So imagine, let's say you extend your right hand towards the mirror as if you're going to try to shake hands with your evil twin. What's happening is the image of your right hand is being reflected front to back. That is still your right hand. But why does it look like it's the left hand? This actually gets into an issue of how our brains work. Anytime we see a living object, we instinctively will do a threat assessment of it. And the way we do that is we mentally shift our own personal location in our brain to where the perceived where the other living object is. So we quite literally mentally put ourselves in that person's footsteps in order to try to imagine how they could be a threat to us. And we do this very quickly, and it's all very instinctual. But what happens is your brain doesn't flip you front to back. It instead walks around and rotates yourself 180 degrees to do that. And then by doing that, you say, oh, that's got to be my left hand now. And so then your brain says, oh, I must have flipped right and left. But that's not the case. If you think about it, you're not flipping up and down. It's only right and left. And it's because you're taking yourself out, mentally walking your own body around the mirror, having to do a 180-degree spin in the process to match what your reflection looks like. A way that you can kind of convince yourself that this is what's happening is if you have available some sort of like a nitrile glove is really good, or if you've got like those rubber gloves that you use for if you're washing dishes or something like that. Anything where you can flip it inside out. If you go and put that glove on your right hand, and then you say, okay, I need the part that's, and then say, stand in front of a mirror. If you say, okay, I need the bit that's farthest away from the mirror to end up being farthest away from the mirror, what you'll do is you'll grab the cuff of the glove and pull it so that you end up turning the glove inside out. But then if you try putting it on your hand, you'll realize that it fits your left hand now, not your right. So that's what's going on, is that you've basically rotated yourself around in your mind 180 degrees to put yourself where you see your reflection. And then you say, oh, in order to fit the new glove effectively, I have swapped my right and left hand. There's an awesome video that you can find on the YouTube channel Physics Girl, where she does all kinds of great special effects to help show that if you want to follow that through a little more.